This question actually comes from an ATAR student, not an IB student, but because ATAR doesn't really test you this level of understanding, but IB will, I'm putting this out as an IB video. And so the student was asking me, why does an addition of one extra electron cause this massive jump from 100 to 181? And the short answer is your data book's not really giving you sort of accurate answers about this. It's just giving you some relative values to compare. Okay, and so just going into the details of that, first of all, there is no real boundary for atomic and ionic sizes. There's no real boundary of where a magnetic field starts and ends, or gravitational fields, or electron fields for atomic ionic radiuses. And so that's one issue, that there's no real definition of that. And so what we're saying when we're saying ionic and atomic radiuses is we've just measured the size, the distance between the two elements in a bond. And so that's what we're saying size is. And so we're not really saying ionic, it's not really an ionic radius, atomic radius, it's just the distances between two in a bond, which is an issue. Okay? And so a lot of the scientific evidence, it's actually done in angstroms. So you just need to times it by 100 to get these numbers here, like this 140, that's actually 140 picometers. And just as a side issue, you'll see that there are large jumps initially, and then the jumps get smaller and smaller. That's due to convergence of the shells. The shells get smaller and smaller. The distances between the shells get smaller as you get, as the energy levels, the shells increase. Okay, so this one comes from one of the journals because it has a good diagram of the sizes. And so what the atomic and ionic sizes are actually about, it's actually the positive attracted to negative in three-dimensional space. And so because these anions are so large relative to the cations, they are repelling each other, and that's the only effect that you see. And that's just for this lithium chloride situation. I've put the electronegativity differences because some of the explanations like to talk about the degree of ionic or covalent character, but I don't think that's as clear as just looking at the positives attracted to negative and how close those pos and negs are to each other. And so if it's actually more of a similar size, so these two are much, the fluoride is much smaller than the chloride, you actually get the two, these repelling as well. So the electron clouds of the cations and the anions start to repel each other, and that gives a much larger distance than you would expect. And so they call that double repulsion in the journal reference that I've got there at the end. And so you can see that this has got actually nothing to do with the size of the ionic or atomic radii. It's got to do with the interactions of the negative clouds against each other and other things that are not even included. So the size of the chloride ion is affected by something that's not even chloride, and it can be a variation of different metals as well, and that's all going to affect the size of the chloride ion. And so what you're going to see, as you'd expect, is quite a lot of difference. All right, so the data booklet's gone for 1.81, but even within this one journal, there's quite a range. So that's at least it's maybe a plus or minus 10 here if you're going for that value. There's a 10 difference there. And so there's differences in the types of compounds, in the methods, and the calculations. There's theoretical calculations. So within that journal as well, you can see there are some, huge differences, like 50. And when you're doing an analysis and you're saying, well, that goes down by 4, you could cherry pick some data and get this one to be, one of them, the complete opposite by 50. And so this one here is completely theoretical and it's gone up, whereas this one would be experimental. And so you can see there's a lot that's not said in your data booklet, okay? And so the takeaways are the English gets in the way. It's not actually ionic or atomic size. what actually counts is the experimental evidence. And the experimental evidence is not the atomic size, it's the distances that they are between each other. And that's not even taken into account when you have a cation and an anion. Where are we drawing it halfway, or how do we determine how far the chloride ion is bigger than the sodium ion? And so we're looking at numbers all the time in scientific evidence. So your data booklets are not telling you the plus or minuses, which are quite huge. They're also not telling you that this is completely uncontrolled. This is a completely different method between these two. And so that's a fault with those as well. But you still use the data booklet because we're still trying to get a general comparison. And so there's those errors that you just need to be aware of them. If you're getting confused by certain things, you need to go back and look at the scientific evidence. And they're the references. Hope that's helpful.